We're very happy to have Michael Trott here, live and in person, all the way from Denmark, and he's going to tell us about the Geometric SMEFT. So please.
Hey, thank you for the chance to drop by and speak in person. So as I was just saying, this is going to be a discussion on the Geometric SMEFT, and this kind of, you'll see the basic point is that it's a description of some curved Higgs field spaces that once you understand they're there and you start to formulate your physics taking that into account, makes a lot of things very straightforward. And that's why there's a big number of papers suddenly appearing of this form over the last couple of years. And the names are color coded with the pictures here, and the people in black and white are postdocs that are still looking for permanent roles, so or grants, and they're doing a lot of good work. And then even master's students are now getting involved. It's something that they can do as well. And this is a master's student that Tyler worked with in Denmark that was doing a paper just this fall. So one of the things I want to get across to you is why it's so simple to do this once you basically adopt the sort of conceptual points I want to say and make clear to you at the start. So please ask lots of questions to make that clear. And then once that's clear, I think everything else will follow quickly. So what is this geometric SMEFT description? So first of all, I want to remind you very, very quickly about the SMEFT, just to kind of remind you about it in the sense of illustrating some of the challenges it has, which this reformulation in some sense of the physics starts to address. So the SMEFT is happening for a very basic experimentally driven reason. The last 10 years, it's getting a lot of attention and people are doing a lot of work on it simply because of what we found at Elixir and what we didn't find. So what we found was a particle, which is about 0 plus as we can see in terms of experimental verification. And just, it's clearly a resonance bump with 125 GeV. It has very Higgs-like properties. And at the same time, what we didn't find was a whole set of other models that had specific features that they've looked for in very consistent and really kind of quite systematic experimental searches. So this is not totally conclusive that anything could, sometimes things can slip past these search windows. But what they've done is they've done a ton of model searches where they basically look for specific features, bumps, and other resonant features, and non-resonant features. They didn't see it, and these are exclusion plots that they placed for all these different models, which are listed going down, and that's a log scale on the bottom. So around 125 G, we found something which is particle content to incorporate into our field theory description, and we also have these exclusion bounds being pushed quite thoroughly now out to about a TeV. In many, many, many cases, it's becoming a more comprehensive statement over time. And so there's a basic separation of scales that we can use to build an effective field theory description. And that's what this SMEFT is about. And that's why this SMEFT has been taking off. And people are doing a lot of work on it, including the experimental collaborations. So down here, we have masses of the electric scale states, including this Higgs-like resonance that we found. And they're around 100 GeV. This is the more massive states. And up here, we now have hopes for physics beyond the standard model in the rose-colored region, which we have rose-colored glasses still hoping. It's a loop factor about the Higgs mass. It's reasonable to hope that there's interesting physics going on there. And we don't have perfect reach into that region, which would be most interesting, TeV to couple TeV. So kind of that's the sweet spot of where the SMEFT techniques are most useful because the perturbations will be big enough to actually possibly see something. And that's also where a loop factor above the Higgs mass, there's very good reasons to keep looking as hard as we possibly can for physics beyond the standard model starting to show up with these sorts of techniques. But that separation of scales, those two shaded regions being separated as they are on a log plot, means that there's a parameter that's less than 1. And that's the ratio of essentially the BEV divided by the mass. And that's being less than 1 is incorporated also in our field theory description when we do the SMEFT, as well as assumptions about the observed scalar being embedded in SU2 scalar data. So this is good, and this lets us do all sorts of things like do combined model searches, lets us kind of reformulate the experimental program from being assume the model, do the study, get the exclusion bound, move on to the next model, to doing something more global, where we do global combined studies for a bunch of operator searches all at once, put them together in a way that's consistent, and then we can bound many models all at once. And it can also let us bound non-perturbative effects. And it's because then essentially these deviations have to look like local contact operator perturbations, perturbing the standard model predictions due to the decoupling theorem. Just to quickly remind you of that, to close out why this SMEFT is taking off, and then also to illustrate some of its challenges. We can't get a search out to that heavy mass scale in that rose-colored region, then the dependence on that mass scale because the decoupling theorem is simplified. It appears as inverse powers in perturbation around the standard model prediction, inverse heavy mass scale squared to the 4th power, up to the hierarchy problem where it appears in the dimension 2 operator and can be absorbed into the observed mass that we see for the scalar. This basic dependence on the heavy mass scale being sequestered into the denominator is the point of the effective field theory interpretations, and then the numerator can have various kinematic invariance depending upon what you're measuring. And then we get to the usual SMEFT. And this is usually where SMEFT talks basically set up things, and this is the SMEFT. And then we have a Taylor expansion with dimension 6, and so on and so forth, where we have higher operator forms with long distance propagating states and their interactions. And then we have Wilson coefficients divided by cutoff scale. And this is a well-defined field theory that we can systematically improve our predictions and just interface with the data. Now, what I want to get to you across in this talk is there's an assumption that is kind of snuck in when we do this sort of formulation of the theory. This, is you'll understand in a moment, is actually also a linearization of some structure that's there in the field theory, which is actually some curved Higgs field spaces that are around. So it's something that's happened here, which when you just formulate the theory bottom up and write down the operators, kind of sneaks in a little bit. And we're going to make very clear how it snuck in and then how to reformulate things to get a little more out of our ability to make predictions. So, and it'll help us with a bunch of challenges that are also there in that basic straightforward formulation. So what are the challenges? Well, one challenge is that basically there's just a lot of parameters. Okay, so if you look at the number of parameters at dimension 6 alone, you count them. We did this many years ago, and you get to this 2,499 kind of famous number. Most of it's in the fermion indices. So 1 versus 3 fermion indices, you see you go up from order of tens to order of thousands. And that's just because 3 times 3 times 3 times 3 is a big number. And that hits all these 4 fermion operators. But then there's also a whole bunch of operators that don't have fermions, just pure field strengths or pure Higgses or derivatives on Higgses. And you can count their parameters too. And also there's basically field strengths that appear, and then things that have to do with like anomalous couplings, fermions to gauge bosons or Higgses. But that's what happens at dimension 6, and you count the parameters out, you get to this big number. Now, you might at that point in time just give up and just say, forget it, I have to assume the model because that's too many parameters to engage with and interface with the data. That is not necessary, and you actually find when you look at these fits that experimentalists are doing or theorists are doing, that they actually come out with about 30 or 40 parameters they're fitting to simultaneously. So what's going on in the sense of 2,499 being reduced to 30 or 40? There's a number of things going on. So usually there's some flavor assumptions that people are making in terms of how they're interfacing with the data. And of course, since most of the problem is in the fermion flavor indices, that can of course tame a lot of the problems. But it's better than that because it's not necessarily just that you're assuming that those flavor structures are there in the theory that you're looking at in terms of constraining from data. It's also that the standard model has a lot of soft broken symmetry patterns, including flavor violating patterns. And even if you just interfere with those, if you get a dimension 6 perturbation, that also knocks down the number of parameters that appear very significantly because it's very hierarchical flavor changing effects in the standard model. So just interfering with the standard model acting as a projector kills a lot of parameters because the parameters are associated with flavor change through the fermion indices for the most part. It's better than that even because narrow bosons in the standard model, by which I mean the gauge bosons, I mean when you interfere with things like this with 4 fermion operators, you get further suppressions proportional to the narrow boson width for lots of reasons of phase space, which they can actually look at experimentally. So there's a whole set of things to do with the structure of the physics of the standard model alone, which is in this game as to why the number of parameters that appear in these dimension 6 fits are being reduced to tens as opposed to thousands. And you can choose the data you use in your global fit, which is also something you can do to be smart about such effects. So it's not a disaster intrinsically, but you could ask yourself the question, if that's how it is at dimension 6, how bad is it at dimension 8? Right? Those subleading terms are around. What about cross terms? How many parameters are there when you start to even go beyond leading order to know what is messing up what you think you're learning from the data, even at leading order? Even with all this reduction to tens of parameters in dimension 6, the subleading terms exist. How bad is it when those subleading terms are not ignored? That's something that is kind of a relevant question in this physics program, which we can now answer in a lot of cases as to how things work, as you see. So it's not just the number of parameters, it's what the parameters do, because they kind of mess with our expectations. Okay, so here's an example. So when we go from the weak to the mass eigenstate basis, we have usual rotation in the standard model, but now we have a modified rotation involving a Wilson coefficient times v squared divided by lambda squared. This is suppressed lambda squared for these Wilson coefficients here. So that changes kind of what you mean by your eigenstates, your mass eigenstates. It's not out of control, but you'll notice that there's a strange thing going on where you have this change due to this Wilson coefficient proportional to v squared. There's a correlated change in the angles associated with the same Wilson coefficient that also appears changing the mass. There's another Wilson coefficient appear modifying the mass. And then you have covariant derivatives, and then here you notice there's barred parameters. For your purposes at this point, those are canonically normalized parameters where you canonically normalize the theory, including dimension 6 corrections. But you'll see in a moment, those will become interpreted as the essentially curved field space Lagrangian parameters. But for now, let's just consider them canonically normalized. The canonical normalization that we're derivative in the fermion has, again, a correlated shift in what you mean by the electric coupling and the GZ and the sine angle again. And it's this Wilson coefficient appearing all over the place proportional to V squared. So there's some correlated shift in the physics happening here associated just with dimension 6. What about dimension 8? What about cross terms of dimension 6? How much of this rather complicated story is going to get even worse when we start to think about the subleading terms? But notice that all the complications are proportional to the VEV in this particular slide. So that's kind of the clue, right? So we want to think about what's going on with the VEV and how the VEV perturbations are coming about. So we also need to assign numerical values to those Lagrangian parameters, whether they're barred or unbarred. And the way we do that is we measure some things and we use those to infer some numbers, which we assign, and we then make experimental predictions once those numbers are assigned to the parameters of Lagrangian. Usually it's just the standard model gauge couplings and parameters, but now there's Wilson coefficients. We also want to have adopted numerical values from some sets of measurements. And so you have to do correlated shifts of things where you basically have things that usually in the standard model are just interpreted in a simple way, and you have a combined effect of a bunch of operators occurring all over the place. So this is an example just involving the VEV. You want to assign 246 to V when you make predictions, which you do in standard model somewhat straightforwardly, and then do perturbative corrections. That's measured at a low scale in the case of muon decay. But now we have operators interfering with what's actually being measured at the low scale. You can modify that vertex. There's also a 4 fermion operator that can just sit there. And then that combination is what you actually measure. Now, if every prediction you made involving the VEV was that full combination, it would not be a complication. It would just be all absorbed into the number. But since we make predictions where it's just really dependent on V and not about how we measure V for muon decay, then you have to correct for when you use the numerical value 246 by popping out all those other terms. This combined thing you'll see appears in the fits, it's dimension 6. But there's also dimension 8 effects, cross terms, and all of this redefinition of input parameters needs to happen too at subleading order if we're really going to understand what is screwing up our understanding from the data just at dimension 6 when we do an inference. So a lot of that stuff is also proportional to the VEV again, but we need to basically be able to understand it systematically. And you'll see that if you think of it the right way in terms of this geometric approach, we not only have this sorted out dimension 8, we have it sorted out all orders in the VEV expansion parameter now. So that's kind of nice to have in our hands. So this is kind of the state of the art in terms of what people are doing at dimension 6 now. So they do linear interference fits, and what they do is combine a bunch of data and constrain about 40 parameters. Parameters are listed at the top here, and they're split between where they basically appear. A bunch of them appear in electric precision data, which is combined in here, left data interpreted, left 1. There's diboson data, there's all sorts of things to do with Higgs cross sections that are being measured, and then there's some top part data that's being incorporated here as well. What this is just showing you, and I don't want to dwell too much on this plot, is there are hierarchical constraints. That's a log scale again. Some things are very constrained, other things less constrained. But what is always constrained is some combination of the Wilson coefficients, right? These are color-coded with how much the Wilson coefficient is basically dominating some combined direction in the Fisher matrix once you inverse it and basically find the constrained directions. And there's always combinations appearing. So the Wilson coefficients appear in a sprinkling of all over just at dimension 6. And again, what about dimension 8 messing up this story? Right? I mean, what about those effects? Do we want to fit to dimension 8, or do we want to basically know what the things that dimension 8 can do to kind of mess up what we're interpreting from the data? Because we're really starting to get interpretations of what we think is actually in terms of constraints from the experimental measurements we even have now. As things get forward in the future and become more precise, we better be serious about what we're actually learning to make sure we don't fool ourselves. So this is the state of the art, and it was one of these things. Well, I don't dwell on this too much, but we'll get back to this in a minute. Okay, so one thing you saw on the previous slide was individual Wilson coefficients. So one thing I want to get across to you as well is when you start to think geometrically, you start to step a little bit away from the specific operator representations and the Wilson coefficients times the operator representations. You start to get things like this. You'll see this example a lot. And by the end of this talk, you'll get very clear as to how all of the physics is getting into this sort of equation. What is this? This is essentially a perturbation in Higgs to gamma gamma. And it's being described geometrically in the way you're going to understand in a moment. And what's appearing here is essentially a kinematic transfer function, which will be characteristically the case, kinematics, and then something scaling the kinematics. And that's something you scale the kinematics by is geometric. It's always going to be geometric. That's kind of a key lesson here. It's independent of the Higgs, that lesson. It really is a general field theory lesson. If we want to, we should probably postpone that talk to later. But what's happening in this particular case is Higgs to gamma gamma. There's a Bilbine here, which is a square root of a metric I'll introduce, which is canonically normalizing asymptotic Higgs state. There's variations with respect to metric I'm also going to introduce. And then these canonically normalized gauge couplings and parameters are also appearing, which I've told you before we can interpret geometrically. So we're going to interpret them in terms of these geometric field spaces. But that whole thing is something which is geometry. Geometry defines all the objects built in there. And you're basically, once you have that in mind, you basically get this sort of idea. Kinematics times geometry is what the amplitude perturbations really work like. And that's a little bit stepped away from individual operator representations. Geometric structures like this are things that will stick around when you do field redefinitions to move around the individual operator forms. But you'll always have a geometric representation. So it's closer to what's actually appearing in the amplitude. The operators themselves can be kind of redefined away with equation motion effects. Whereas now this is like kind of a sweet spot in between operator representation, which you get expanding these things out, and the actual amplitude and what appears there. So think kinematics times geometry going forward, and you'll see that's always what's going to appear. So let me explain to you what geometries are there so you can understand that statement and how powerful it is. Is there any questions yet? Now we're basically getting to the conceptual step that you need to take. Okay, everyone's happy. Good. So what we needed to do to find this sort of geometric description was just to step back a little bit and think a little bit harder about what we're actually finding. We found this bump in the data, but it has a specific way that its physics works in the standard model. And then once that's basically embedded in an infinite tower of higher dimensional operators, that's what's going to lead to a lot of the geometries that are there that you'll see. And that's what we basically understood that this is the key aspect of the organizing physics. So what did we actually find? Well, we found something which is very consistent with this story, which is what the Higgs is in the standard model. As far as we can tell experimentally, it's perfectly consistent with this story. So it's a field H that has 4 components. And then when it gets on back an expectation value, the other fields, depending on how strongly they're coupled to that field, they get masses. And when they propagate through space, interact with Higgs condensate, they slow down. And what happens more importantly than that is basically you get combinations of gauge couplings in Lagrangian terms that you initially write down in a certain form, which become the useful combinations of gauge couplings in Lagrangian terms in general, like masses, which actually appear in lots of experimental measurements. Now, going forward, green blobs are going to be the VEV whenever the VEV is inserted. Okay, so in the standard model case for the Higgs, it's very straightforward. You know this. You start with D less than before interactions with this form. The condensate, you expand around that background, and then you get combinations of things that was there initially, which are useful to interface with the experiment. That happens in a very specific way, where higher dimensional endpoints, like more and more fields, are descending to lower fields, lower number of endpoints in the field connections. Okay, so you have, for example, the kinetic term for the Higgs, and it has 2 scalar fields and 2 vector fields. 2 green blobs mean 2 VEV insertions, so a 4-point function initially descends to a 2-point. And then you have to rotate to the mass eigenstate basis to basically get to the useful combination of the Lagrangian parameters, the mass of the W and Z in this case, which appear in lots of different experimental measurements. It also happens with the 3 points. The VEV is inserted, and then you go from a 3-point to a 2-point. And again, you get something proportional to the VEV, which is a useful combination of things that appears in the experimental measurements. Very straightforward. The only reason that we don't talk a lot about high endpoints descending to low endpoints in the standard model, and we don't talk about geometry for the reason you'll see in a moment, is because there's an accident of normalizability happening here. We basically have a limited number of endpoints to start with because of renormalizability limiting the mass dimension of the operator forms we write down. So in the case of the standard model, D less than or equal to 4 due to normalizability, and you get through the VEV useful combinations of Lagrangian parameters. When you start to do infinite towers of higher dimensional operators, what you get is you basically get dimension 6 perturbation, for example, for Higgs to gamma gamma, which in the standard model is the loop. 1 VEV happens for the Higgs, you get a perturbation. But you can also get that at dimension 8 and 10 and 12 and 24, whatever you want. And you can also insert symmetry generators. And all of those endpoints descend down to just a perturbation of the 3-point function Higgs to gamma gamma when you actually have this infinite tower around in terms of the higher dimensional operators. So now, because renormalizability is not there in the sense of the usual classical word of normalizability and the interpretation of normalizability, you still have the ability to normalize the theory and the EFT sense, but then you have a lot more field space connections to start with. And then they descend down to a 3-point function, all collapse down when the Higgs takes on its VEV. Now, when that happens, they have to appear in an amplitude to perturb this, one combined thing that happens in the amplitude. And it has to be that what appears in the amplitude is independent of how you coordinatize the scalar, because it's just a choice we make, which doesn't change fundamentally something that's measurable in physics. And you would also want it to be something which is field redefinition invariant if you have a very effective basic formulation of the theory, right? So the key point is that what can appear, which is independent of how we coordinatize the scalar field, that characterizes this physics and this field redefinition invariant? And the answer to that question is geometry. So there's a geometry addressing this amplitude that multiplies kinematics, and that's what I showed you before. And it has to be something which is basically a description which is independent of the coordinate choice for the scalar field and also field redefinition invariant. So it has to be something which characterizes some aspect of the physics which is independent of those coordinate choice things. And it's just like when you have a space, a physical space, and you want to have a characteristic of things about that space, which is independent of how you write down coordinates for that space. Those are geometric properties of the space, its curvature. So now there's going to be a field space, which we're going to have the geometric properties of that space appearing in the amplitude. That's why conceptually you should be very happy with what's actually happening, because it basically has to happen for it to be independent of the coordinate choice for the scalar field, and the field redefinition invariance appears in these geometric objects. Okay, and then we're going to get, again, useful Lagrangian parameters, masses, and that sort of thing, but it's going to go and appear through a geometry. Is everyone happy? That's why this is happening. We're going to now define this object in red, a particular geometric structure, and these other objects in yellow are another set of geometric structures, like I told you. And that's why it has to be geometric, addressing the kinematics. And that's the argument I just gave you. At least for the scalar field, that should be clear. So these are the geometries. Okay, so the first one people realized was there. And this is something that's a very old story. It goes back to like Planck physics and that people knew in cosmology, thinking of target space metrics. But what is old is new again, and it's kind of really applicable when there's a Higgs around, for the reasons I just said. So what you do is you basically look at the kinetic term, and you say, well, can I do field theory with a general function here, where I open the indices for the kinetic term, which usually this is just contracted with I and j contracted with one another. And I'm going to let it be a general scalar field because of these background fields that are around the Higgs that can take on back from expectation values and become green blobs. So if that's around, can I do field theory like this? And the answer to that question is yes. Russian was asked that general question a long time ago, and it is yes. And now we're going to use a Higgs field written in terms of these real scalar field coordinates, 1, 2, 3, 4, which is what these indices run over. This is going to be the square root of this object, which is really a metric. It's a distance in a field space. And this is going to be, it's really a build line. And then when there's a tilde, there's going to be the v squared over lambda squared absorbed into the Wilson coefficient. Okay, so it's the expectation value of the Higgs because that's the scale associated with the scalar dressings. And then that's what appears perturbing these ones in the diagonal, which are the case of standard model. Now, what's interesting about these ones on the diagonal is also this trivializes the Kronecker delta, which is what we usually write. We never bother to write, ones with a Kronecker delta, so it's kind of trivialized. But that also trivializes the geometry. It makes it a flat field space. As soon as you have these perturbations of one around, and these are small perturbations, this is a well-defined inverse and well-defined square root, then that leads to geometry because these perturbations, if you calculate the Riemann curvature tensor from this object, basically leads to a curvature that is characterizing this object. Okay, and then aspects of this projected appear in amplitudes. So we've thought about this, other people thought about this, but this is the first field space people realized was around. Now, this is not a physical curved space. This is an interaction field space. Okay, this is defined by the interaction terms in the Lagrangian that you write down. And it's going to be characterized always in red, what you see. We're going to systematically highlight these things in color because you're going to see there's lots of these field spaces around. And the intersections of these field spaces is what actually appears in the amplitudes. So this, yeah.
Sorry, I'm a little confused about the square root.
Yeah.
If you were doing this for a curved space, you would have an additional rotational symmetry, and you would have basically an infinite choice of what you meant by the square root.
Not unique square roots.
Right.
Yeah. So the thing is, there's small perturbations around the standard model is the key point. So there's a well-defined square root. And you're right in general. If the perturbations are large, then absolutely correct. But when the perturbations are small perturbations around a flat space, then there's a well-defined square root, which is what this comment is about. It's positive semi-depth the matrix. Okay, so there is a unique square root.
Well, my worry wasn't so much whether the square root was unique, but that if you're defining a field line in general relativity, for instance, you have the freedom of a local Lorentz transformation on that. And is there anything like that here?
So when you think,
ever matter?
So when you think of just this object as a general object, then your comment also applies.
Right.
But what's happened here is we've basically taken this object and we've imposed a symmetry, which is leading to the ones in the diagonal for the case of the standard model. And these operators have a bunch of symmetries associated with them. So we've gauged a symmetry here. And that's why it's not all entries being random. This not only does it have perturbations, there's a very specific pattern of the perturbations consistent with the symmetries, which constrains the transformation properties. And in the general case are there that you're talking about.
Okay, good.
But you're absolutely correct in general. It's just we have small perturbations on our hand and gauge symmetries, making it so it's a little more predictive.
Okay.
Good. So ask more questions, please. The yellow here is another field space that's around, which we realize when we gauge fix the theory. You'll see that at the end. So what is W here is a generalized Yang-Mills term. Okay, so this is W 1, 2, 3, and then a B field all combined up. So these A and B's run from 1 to 4. And just like the case you just saw, this is a kinetic term also for the vectors, right? You can have a general dressing as a function of the background scalar field. That can be around, and it's different than the one you just saw because the different Wilson coefficients that appear can basically lead to different curvatures, although there is still a curvature associated with the perturbation around the standard model, which is again a well-defined inverse perturbation. Again, you get these tildes because it's b squared over lambda squared. That's the scale associated with these field space geometries, and this is a different field space geometries that's around. Okay, so this is around, and I don't want to belabor it too much. It's going to be highlighted in yellow for what you see going forward always, because it actually has a specific role in terms of what it leads to in terms of the predictions. So now we have 2 on our hands. But with those 2, if we think of them as now general objects like you were asking about, we don't have a specific operator representation of perturbations, we can consistently transform from weak to mass eigenstates. And just by making sure that there's a well-defined generator associated with an asymptotic state, which is a mass eigenstate field, we can basically impose that with that consistency of the transformation requires you to basically have a self-consistent solution in that transformation, and that those generators are self-consistent. And what that means is that you basically then get these barred couplings that in the case of the dimension 6 operators were just canonically normalized field couplings, which now are the things sitting in front of the generators. And this you should consider at this point to just be a generalized object, that if we knew it, we could have this consistent transformation to weak mass eigenstates. But there is a bar coupling of this form related to these 2. There's a well-defined GZ that we can actually choose, which has this combination of Lagrangian parameters and also with the electric charge. And now the masses here, you'll notice, are depending upon this red field space metric. But if we knew this object and this object, we would know these things at all orders. And there's also a massless photon. Now, the interesting bit is that the generator transform being self-consistent means that you actually have to introduce another angle. That's why this is here as well as this. And these 2 angles you would not see until you start to think this way, or you go directly and brute force calculate to dimension 8. So in the case of the Weinberg angle in the standard model, it's to generate at dimension 6. It's to generate in the standard model, but at dimension 8, it's actually distinguishable and have consistency of the mass eigenstate transformations from weak eigenstates. You have to introduce 2 mixing angles in field theory. Now, if we knew all these objects, we would be in business for all orders results, at least associated with these Lagrangian parameters, these geometric Lagrangian parameters. And we do know those objects at all orders for another reason that's kind of nice in the physics. These are the answers at all orders for these 2 I've introduced so far. These are equal signs. There's infinite series here. So first of all, why can we write these down at all? Well, there's a very simple thing going on, making it so that you can write down these objects in a complete form. You have scalar fields dressing certain kinematic transfer functions, and you have possible symmetry generators. And that's what you have. So you have an SUN fundamental and its symmetry generator, and you're contracting those indices. So the SUN fundamental with other SUN fundamentals, Higgs is contracting with Higgs's and their indices, or through a generator. And if there's just through a generator, then you're going to get completeness relations that you're used to in the case of the Pauling matrices that are for the SUN theory. And they'll reduce down to delta functions eventually when you have, generator times generator. And you basically, yeah.
Go ahead and finish.
Okay, yeah. So these generators will reduce down to delta functions. And that's why you don't have arbitrary complications here. Essentially, you run out of the ability to contract up indices differently, and you end up basically being h dagger h towers or phi squared towers on top of what you've already written down, essentially out to dimension 8. Let me finish and then ask your question, because I might answer it right now. This is not a Christoffel. This is an aspect of the symmetry generators in the scalar field real representation that we choose when we do this formulation. But it has indices and it contracts with the scalar field. And if you look, there's not that many things written down here. There's a couple things written down, and then there's h dagger h or phi squared towers on top of that. And there's infinite series of that form for the reason I just said. And also with this other object, this other field space metric, it's the same story, just a little bit more complicated. There's still symmetry generator insertions through these gammas, And there's a little bit more structure here, but it's not arbitrarily complicated structure. It's basically a little bit of complication up to dimension 8, if you look at the dimensionality of what's there. And then things become H-H showers on top of that. And that's quite characteristic of the physics here, which is actually a very powerful thing because it lets us write down these objects at all orders. And if we know them at all orders, and we also know these, then we can just Taylor expand to get these answers at all orders in the Bev expansion, the V squared over the M squared expansion. Question now?
Yeah, I just wanted to see if I'm following. So this
Yeah.
is all at order 2 derivatives. So you're not considering any terms with more than 2 derivatives, correct?
Yes. So there's issues of the geometry when you start to do generalized derivatives, right? So when you start to do more and more derivatives on the scalar field, then you have to, there's technical issues there, which you probably know, which is how you define the geometry associated with more and more derivatives. So there's an assumption here, and really there's also a math choice here, that we are reducing out derivatives if we can with the equation of motion. So the set of geometric objects that we write down, I'm going to get to that in a second actually, is going to be something where we've taken a specific choice of reducing out arbitrary derivatives that you can write down and extra derivatives that you can write down, and we systematically are reducing out derivatives as much as possible with the equation of motion. Now, when you restrict yourself to 2 and 3 point functions, because of the triviality of the kinematics associated with the 2 and 3 point functions, you can in general do this and reduce out these derivative forms so you're not losing anything. When you're starting to think about higher endpoint functions where the kinematics are less trivialized, then your question is very, very, very relevant because then you have to worry about the higher derivative terms modifying the 4 point functions, which is fine. It can be systematically taken on, but there is, of course, that consequence of doing this sort of field theory formulation we're doing now. So hopefully that made sense, and it'll make a little bit more sense in a moment in terms of what I showed you for the full set of these objects that we write down. Is there a follow-up question, or are you satisfied?
I'm curious. I mean, are you thinking that there's some generalized notion of geometry that would apply once you get to 4 point functions?
Yes. Yes. And the reason I think that is because what you'll find is that so you should start to associate the geometry appearing in the amplitudes with the intermediate quantities, which are field redefinition invariant. So if that's the case, and field redefinition invariance is around, and if everything that's going to be field redefinition invariant at higher endpoint amplitudes, including 4 points and above, then we should always have a geometric understanding on our hands, just because we have field redefinition invariance on our hands. Now, that's a very carefully formulated statement where everything that appears in the amplitude will be geometric, but not everything geometric is field redefinition invariant. Okay, so those two things are perfectly fine. And in particular, the metrics, themselves, the way they appear, those are not themselves field redefinition invariant. But things like Riemann curvature tensors are, and they also appear in 4 point amplitudes. So this is partially work that's ongoing, but very much yes. The basic message here is that a geometric formulation of field theory is very useful for interaction terms beyond 3 point functions. And it even is more general than the scalar field, because it really has to do with the field redefinition invariance, what quantities appear due to the field redefinition invariance that's in the field theory, and their geometric quantities due to the interaction terms. So we can go over that more later maybe, and also as we go on. Let me try and build up what objects we can do just with these couple ones I've introduced so far, so it gets a little clearer. So we're going to go Weaktomass eigenstates, and the objects I've defined so far, let us do that for these fields and their couplings and scalar fields. This is the general Yang-Mills term I introduced. This is the gauge coupling, and now this is a scalar field. And the transformation from the Weaktomass eigenstates in the case of standard model, remember, had those ones on the diagonal, a trivialization of the Cronk for delta, which also is associated with flat field space, is what I'm saying. So because of that association with the flat field space, this is actually a simple transformation, which is actually rotation. The matrix that appears there, its transpose is equal to its inverse. It's actually rotation. And then this transformation is quite straightforward and well known. It's just a standard model. And you can interpretively correct this, but this is the straightforward story from Weaktomass eigenstates. You get these sorts of scalar fields and couplings and that sort of thing. And then you get mass eigenstate fields. And it's very much straightforward. Now, if you want to go and use these objects to go at all orders in this transformation, essentially, what's the benefit of this? There's multiple benefits, but one of them is basically the first thing you should ever do when you start to do this stuff is write down the object and then write down the equation where you contract the indices correctly. And usually that's going to be the right answer. So what objects do we have around to transform now to contract these indices? Well, the square roots of the metrics are around. They're well-defined square roots. And if you contract the indices, And if you also think of these as a field line, just define the asymptotic states of the eigenstates of the system, it makes more sense to think in that way. Then this combined operation is no longer a rotation; it's a transformation. It's also canonical normalizing the field theory as it's doing this, going from weak to mass eigenstates. And there really is nothing else in the game essentially that you could write down that would lead to canonically normalized asymptotic states. So you're just contracting indices as you do, and if you knew these objects are all orders, you would know these transformations at all orders in the field theory. We do know them all orders, I showed them to you because they're very simple. That's an example of how it's useful. And there's generators here. So we probably should talk about generators later. If you want to look at the more mathematical classes, which are pretty cool. But these little gammas were not the big gammas that you saw in the metrics. We basically are using generators on real field space. It's quite straightforward, but there's a great benefit to using real coordinate system for the scalar field and then using this generator set, which I can explain in a moment. And you'll see that this verb of the metric improves there as well. Okay. So now if you look back at this, which I was pointing to at dimension 6, meaning it's a bit complicated, what the hell is going on here? You can now understand what you're seeing. All of these things highlighted, which I was pointing to before, associated with the bev, that were a little complicated at dimension 6, what they really are is that we've basically described a curved field space set of Lagrangian parameters, and then we've linearized out to dimension 6. And that linearization is like choosing Cartesian coordinates for something that's a curved path in space. So you get a correlated transformation projecting on those axes of how you define things, and that's why that Wilson coefficient is appearing all over the place. It's a correlated projection. But what's fundamentally going on here are geometric Lagrangian problems. I showed you these guys just a moment ago at all orders. And that's why essentially this structure is in the field theory, and why it's as complicated as it is. And now it's not a problem to go to dimension 8. We have solved the system and we know what at dimension 8 or 10 or 12. It's a solved problem. At tree level, these Lagrangian parameters. We know at all orders these Lagrangian parameters associated with the bev expansion. And the reason is because we're starting to think of the right Lagrangian parameters, which are the curved field space Lagrangian parameters, which we now have on our hands that understand. Right. So it should be clear what the idea is. What we do is we take this straightforward linearized approach and we essentially reorganize the physics. It's still the SMEFT. But what we do is we basically look at kinematics times geometry. We want to define and formulate the theory as much as possible in that way, which is consistent with what's going to happen at the amplitude level at the end of the day. So we pull out all the scalar field dressings and all the symmetry jitter insertions, all that structure which is associated with the bev. We multiply it by specific kinematics that has to do with Lorentz index interactions. Now, there's an issue with this operator form, the derivative acting on the scalar field, because it has to do with both of those things. It has to do with scalar fields and Lorentz indices, and they're grouped essentially with derivative expansion. So what's nice here is it's also basically pulling apart the two expansions that are in the field theory, the one associated with the bev, and then it's the derivative expansion associated with kinematic invariants, which are not the bev. And those also are two expansions that are around in predictions. So it's kind of organizing the theory a little more systematically, pulling apart the expansion parameters that are there. So if we do this, then we're doing a geometric formulation of the theory, and there's a great deal of benefit to doing this. I've shown you some benefits. Let me show you some more benefits now. Okay, so first of all, there's not that much that you need to actually understand in terms of these objects when you go in 2- and 3-point functions, which is where a lot of the phenomenology descends from 2- and 3-point functions. Resonant regions of phase space are very dominated experimentally, and if you know 2- and 3-point functions, you basically can describe those. I mean, kinematically resonant regions of phase space, but with resonance bumps. Even if you can't reconstruct the bump, it still dominates the phase space. This object we talked about a lot. It's constructible in the sense that if you knew the Lagrangian, you can take variations and you can pull it out and define it. There's not much. There's just these two guys that we talked about before. We're talking about CP even up to 4-point functions in terms of the geometric structures we need to write down. Of course, the potential is a pure function of the scalar field. That's kind of trivial, but it's pretty straightforward to write down. But there's also these guys. So there's basically scalar field dressings of 3 field strength interaction terms. And there's also this, which is 2 derivatives on scalar fields multiplying a field strength. And this object and this object, if we knew them combined with these objects, are basically what we need for a whole bunch of phenomenology. There's also the phenomenology involving the fermions. So you need the generalization of the Yukawa coupling, and you basically anomalous couplings of W's to these fermion pairs. But it's just 3 field space connections, including dipole operators. And in the case of the gluon fields, you need the same thing, but it's actually simple in the case of the gluon field because this is these indices are trivialized because the Higgs doesn't carry color charge. So these are the 3 objects we need. So if we knew all of these field space objects, we'd be able to describe all the phenomenology in the scalar field expansion, the v squared over lambda squared expansion of the 4-point functions. And if we knew those in closed form, we'd be in great shape. And we already are in great shape because we know those in closed form for almost 2 years. So this gets back to your question, how to formulate the theory. So the fact that I said there's this set of these objects, there was a derivative reduction that happened. So we used the fact that we're reducing the 2 and 3 point functions. We're moving out derivatives as much as possible. And that choice has basically reduced us to that set of objects which will define the geometries. So there'll always be a geometric formulation, you need to an alternative path. But this is basically shuffling a lot of the complications to 4 point functions and above in terms of the kinematics. Okay, but we can make that choice in formulating the field theory, and this is a particularly simple way to formulate things. It's consistent also with how the dimension 6 operator basis, that's the Warsaw basis, was defined. And basically, it's the way we normalized it when we started calculating things, because it's an algorithm of how to deal with derivatives acting on fields that you can actually just write down and follow. So there was a choice here, but it's the standard choice essentially in effective field theories. Reduce out derivatives acting on fields with the equation of motion if you can, including these general field space objects. And when you do that, this is how you benefit. This is the complete set of those that I wrote down before, color coding it. And there's multiple things going on here. So let's again re-emphasize this point. Okay, so at dimension 6, you saw this object had 2 guys, two structures. Dimension 8, there's still only 2. Dimension 10, there's only 2. So you just get h dagger h towers essentially once you have something at lower endpoints or lower mass dimension. You just get h dagger h towers on top of it, which is what we saw explicitly. Same with this. In that case, there's one more at dimension 8 if you look closely at the formula I showed you before compared to dimension 6 in complexity. But then you're done. And just h dagger h towers on top of that. And that's quite generally the case. Once you get to dimension 8, you basically have the structure in the theory for low endpoints. And it's basically because of the completeness relation showing up. There's an interesting beast, which is this one, which is empty at dimension 6 in the Warsaw basis due to the choice reversive derivatives. But inevitably you get it at dimension 8. There's 3 parameters, and there's one more at dimension 10. But then it saturates again. So this general saturation that happens in terms of complexity is quite generic. It's quite generically associated with dimension 8. For this one, you need to go a little bit more up to dimension 10. But you can see the general structure here. What's color-coded here, I color-coded before, and we continue to do that, are what the phenomenological consequences of these objects are. So there's masses and gauge couplings that are geometric, and there's anomalous couplings with W and Z, Eucal's dipoles, and anomalous fermion couplings. But that's what these things do. So if we know these things, we can do all sorts of phenomenology associated with those sort of physical effects. Okay, so that gets you to this plot, which is a very good message and basically something that comes out of this approach. The general number of parameters that appear in these field theories, which as I was saying is one of the problems before, is extensive, right? 2,499, remember that number? This is 3,045 associated with dimension 6 because they've added in the baryon number violating ones with the baryon number conserving parameters, which is the 2,499. This is 3 generations. This is 1 generation. Again, it's the number of generations that causes thousands. But nevertheless, whether it's 1 generation or 3, it's going up and a log plot as a line, roughly speaking. So that's exponential growth in the number of parameters as a function of mass dimension in general in the Hilbert series in this theory. That's bad because that's a lot of parameters at dimension 8. And it's even worse at dimension 10. It's growing incredibly, 3,000 to 45,000 to 2 million. Okay, that's bad. In that badness, there is a nice subset of the parameters associated with the most important phenomenology involving the Higgs and for scalar fields and for things that can actually measure experimentally very precisely, which is associated with the Webb expansion, and resonant regions of phase space. And that's these lines, which saturate in complexity, as I showed you before at dimension 8, roughly, when we need to go to dimension 10. These color-coded were consistent with the previous slide, and you can see that within this incredible complexity nightmare, there's a nice subset of parameters and a nice subset of physics, which is well-defined, and which is tens of parameters, not millions. So if you stick to these sorts of things that you measure experimentally and you develop your theoretical predictions along this line, then you're going to have better control over what you're interfacing with experiment. And that's the difference between studying tails in these EFT techniques, which are associated with derivative expansion, and studying resonant regions of phase space associated with the scalar field expansion. That's why I'm like the biggest possible promoter of let's stick with the scalar field expansion. Let's do resonant regions of phase space measured as precisely as possible and as carefully as possible. And then we'll iteratively span out to look at tails of distributions, but only then look at tails of distributions associated with this behavior. Because there's an n factorial around in those studies. And if you just ignore the dimension 8 terms, it's still there. So you have to be very careful in terms of what you're doing interpreting the data with these distributions going to the tails. So that's what we can actually do when we stick resonant regions of phase space like resonant Z phenomenology at left. Okay. You have an understanding of this sort of thing. Okay, these are bad dressings of anomalous field space connections. If we knew this object for a W or a Z, we can do a lot of phenomenology, especially in resonant regions of phase space with the Z like at left, the Z. So what do we need to do that phenomenology? Well, we need basically this kinetic term with the canonical understanding of the curved field space Lagrangian parameters in there, which we now know at all orders. And we also need this field space connection, if there's one like this around, to add to this term. Those combined describe this at all orders in the event expansion up to loop corrections, which we also have to do. We'll get to those in a moment. So if we knew that, we'd be able to do a lot of left phenomenology. We know those things. When we expand out, this is a one-line answer as to the anomalous coupling of the W, Z, and photon to the fermion pairs. We need to know this field space connection. You have these tau bars here. These are generators in the canonically normalized theory and the mass state field. And it's a compact answer at all orders and the overlap. It's kind of nice. And when you expand it, it looks like this. It starts to look like the standard model ones you're used to, leading terms, leading order. Then we need to know the field space connections go and basically have the perturbations. But it's very straightforward if we know them to do this, because all we need to do is basically calculate decay widths. If we know those decay widths, we can do a lot of left phenomenology. And this is how these guys feed in, these decay widths. Everything's canonically normalized, that's why it's borrowed. And this is basically how we go and calculate left data to dimension 8 with a Taylor expansion. Very true. So what you get when you do that is you get an understanding of like there's an anomalous vertex here. The leading expectation value of the background fields associated with the scalar are the standard model for the couplings of the Z fermion pairs. This is the V squared over lambda squared correction, which is the usual interpretation of left electrification data when you do the Z of T interpretations go away from S and T. And now we can calculate V to the fourth or lambda to the fourth corrections or any term in this expansion we actually have closed form answers for. So we just keep going if we want. What you get in terms of interpreting the data are things like this. You can see these are anomalous couplings like this. And this is the dimension 6 perturbation. So basically you should interpret this as this number times this plus this number times this plus this number times this is what characterizes this term in this expansion. There's two sets of numbers here because we're doing both input parameter schemes. So you can do either one, and you can just do left phenomenology with both sets of inputs to define the Lagrangian terms. This is something people knew, essentially, before this work. This is just how you think about the dimension 6 terms in this sort of formulation. And these are the things that people didn't know before because there was no formulation of the field theory to dimension 8. So you can just basically take this effective coupling and now do the next term in the expansion. It's just a Taylor expansion. It's completely trivial. Like an undergraduate student could do this, but you hand them the formulas in the code. And what you get is these numbers times these guys. There's a lot of cross terms which don't appear in the self-square interactions, like the quadratic terms. There's a lot of structure there that's cross terms. This is stuff that all was there in dimension 6 and then cross terms thereof. And this is the small set of things that happen in dimension 8, which is new. It's not that many things in dimension 8 for the reasons we've already discussed. And we have all of these numbers which characterize this vertex at dimension 8 now. We have it for all the interaction terms of the Z for both input parameter schemes. So then we can just
suppose that I adopt this SMEFT expansion function. I include dimension 6, dimension 8.
Yep.
I can still get the same answer, right?
Yes.
So I'm trying to ask is what's the advantage between your approach and the approach that's including dimension 8?
Well, so you can say in principle, people could have done this calculation
Yeah.
at dimension 8.
Yeah.
And that's true. And in practice, what you need to do that is you first need to write down a dimension 8 operator basis.
Yeah.
And you need to reformulate the field theory, all the transformations to weak to the mass eigenstate fields up to dimension 8. I showed you how to do that elegantly with geometry. You have to do that. And then you have to do all the input parameters from dimension 6 to dimension 8. All of that stuff, you could algorithmically grind through at dimension 8. But no one did it for 20 years for a reason. It's just hard, and it's not clear how to do some of the steps. Like the weak to mass eigenstate transformations are a little non-trivial because of cross terms and how you do the rotations and transformations. And when you do it geometrically, it's just you write down the closed form answer basically dictated by index structures. And then you just have the answer not only at dimension 8 on your hands, then Taylor expand, you have it at all orders. So you could do it group grind and brute force. That's true. But no one did for a reason. It was just going to be freaking hard. And basically this makes it very easy.
Okay, I get about so without your approach, then can I match dimension 8 operator?
Sorry?
can match, let's say, this is C tilde H B
Yeah,
8. Is
that's
that the
right.
operator matching?
Yes, so there's also dimension 8 operator bases that have been written down, one by Chris Murphy and one by a Chinese group.
Yeah.
And these operator forms are actually consistent with Chris's formulation.
Okay, you can match the operator.
It's already matched. Yeah.
Okay.
Yeah. Now there's a little bit of work you need to do that matching because you make choices how to formulate the physics, but it's very straightforward and we've done that in the literature.
Okay.
So, and there's more coming in the literature too, in terms of that mapping. It's very well defined. There's no intrinsic flaw. It just basically, if you do the grind, just in dimension 6 to dimension 8, you can do that grind, and you need to, in some sense, have the dimension 8 operative basis from the grind around for interpretation. But if you want to do the actual calculations very efficiently, you should do it this way. Because you can do it, like left data, it took us 2 weeks to do, 2-3 weeks to do the Taylor expansions once we had the Oliver's answers. No one could do it for 20 years. And it was like, once these answers were on our hands, it was just weeks of work. And it was literally just a matter of realizing that we could do it, which was a much bigger barrier than actually execute. This makes it really easy. And it's also the right physics for a number of reasons you're going to see in terms of even perturbative corrections, which we're going to get to. Good, so then you can start to learn. You start to basically look at plots and you can say, well, what did we thought we learned at the left data with the dimension 6 stuff? How does it change now that we know this dimension 8 stuff we couldn't calculate before? Some things are very insensitive to what you thought you learned. So this is a plot which shows 2 lines, which you probably cannot see very easily, which is a dimension 6 perturbation leading to an overall anomalous C coupling, and then dimension 6 perturbation squared, which is the other line, red and blue, or red and black. And the shaded regions, when you have the other terms which you now can calculate around, you sample them around, and you say how much do you perturb that prediction you were going to make for some specific set of Wilson coefficients which are listed here, the dimension 6 terms. So that's not a big deal. That's kind of straightforward. And when you have a tree level coupling in the standard model, frequently this is the case, although there's times when tree level couplings can also be sensitive to numerical accidents in terms of what they predict. This one's not too bad. What you thought you learned is pretty close to what you're actually learning when you know dimension 8. But this is also true. So with those tree level couplings, you can build up things like forward backward asymmetries. And if you probably know there's a numerical accident associated with the forward backward asymmetry of the Z, and the coupling of the Z to leptons. Vectorial coupling is almost 0, which is the cancellation of the Weinberg angle and the combination of parameters in the standard model, which makes it so that the forward backward asymmetry of leptons is very sensitive to dimension 6 perturbations. So that makes it even more sensitive to these numerical effects of dimension 8 stuff when you're doing sampling. But very strong effects can happen in terms of perturbing what you thought you learned just at dimension 6. If you don't assign a theoretical error for dimension 8, you can get yourself into trouble. And it's also very scheme dependent. Input parameter scheme dependence is what this plot is for this plot. Alpha scheme versus W scheme. This is at 1 TV, which is marginal for using these techniques, but you get the idea. Even if you're doing 2 or 3 TV and you're sampling Wilson coefficients in regions of parameter space, you need to worry about this perturbing what you think you learned just at dimension 6 naively. You can also see it here. This is like what's usually the S and T parameter for an operator interpretation when you project down just to 2 parameters from the generalized parameter space. And the different regions are the red regions versus the shaded regions, what you get just at dimension 6, the usual interpretation, and then what you get when you do basically the full dimension 8 effects. And you can see 2 things. One is basically that 1 to 2 TV can start to converge as the cutoff scale goes up, as it should, because the dimension 8 effects go down. But there is still an effect, and it is skewing what you think you're learning. And this is an anomalous Z coupling, lepton coupling to Z, and then T parameter again.
Sorry, so I'm just trying to understand what these fits are. So you have some a priori restriction on the size of dimension 8.
Yes.
And then you're doing some kind of a fit that penalizes you when your dimension 8 operators get out of that theoretically determined range. Is that what you're doing?
So there is an assumption in terms of the sampling of the Wilson coefficients that you impose after you've chosen the cutoff scale of the theory. So the cutoff scale of the theory is chosen, and then you sample the residual C's that you have with an assumption in terms of how those C's are distributed. That's a perturbativity assumption, and also combined in like the tree loop thing in terms of the Wilson coefficients. And
So you're not fitting to them?
well, what's being fit to here is then you're varying it around the dimension 8 effects, and you're fitting to them. But you're in one case, you're basically using these dimension 8 effects to have an extra effect in the error added in quadratic terms, essentially. It added in quadrature with the other errors.
What it's telling me, I need to understand what you're doing. I haven't understood it yet. So So you've got some dimension 6 predictions, and they depend on some parameter, dimension 6 parameters,
Right.
and you're fitting for those.
Right.
But then you're scanning over some parameters in dimension 8 that are adding errors. So you're treating
That's
those as errors. That's what
That's
you're
right.
doing.
Right.
Okay.
And you're adding those in quadrature with usual experimental errors.
Okay. All right.
So that's these two plots. And here's just a direct sampling of how the shift is affected by dimension 8 effect. Compared divided by the standard model. So just giving you an idea that the dimension 8 perturbations come in and actually shift.
So I presume that the distributions of the dimension 8 operators are centered around 0.
Yes.
So then I'm a little surprised, like in the upper left plot, that it would shift the central value so much.
Yeah, because how the sampling of the other effects appear, it appears through added in quadrature with the experimental errors and the other theoretical errors. So it's not just a direct distribution which is shifting out of 0, right? Because the way it comes into the predictions is basically biased by the experimental and theoretical sensitivity you have for the parameters and how they appear in the first place in the standard model, and also the experimental measurements.
You mean the best fit is not standard?
Sorry?
You mean the best fit value is not the standard?
Yeah, well, the best fit in this case is centered for when those Wilson coefficients are there. Yeah. Now, what you think is the best fit will be perturbed by how your errors are added and disturbing what you think is the case. With just so in one case you have an assumption, which is basically the theory is this 2 parameters in addition to the standard model. In the other case, it's those 2 parameters with extra errors associated with this added to the standard model. So it's not like completely trivially just expanding around 0. It matters how they're added in quadrature with the experimental and theoretical sensitivity, which is essentially a projection in a larger n-dimensional space. So we should probably go on. We can come back to this if we want. Okay, but one important point I think for this is that this is clearly setting the message that interpreting that electric precision data, which is combined in with Higgs data and other data, you have to be damn careful in terms of these neglected effects. And this is going to matter for future collider studies a lot, because electric precision data is really important for combining with all the sort of sensitivity studies of Higgs measurements and sort of thing for future facilities. I think that's clear. How we define the errors associated with these neglected terms and how we learn more efficiently from the data, we're still working on, but we should not just ignore these sorts of effects. It's got to be a mistake. Okay, we can also look at the Higgs, and we look at this a lot. So now this should be very clear to you, very straightforwardly understood. This perturbation of this 3-point function, right? You saw this a lot. Now, what we did initially was this is the first time we could calculate beyond quadratic terms actually full dimension 8 results. And we just wanted to basically ask the question, what do you actually get with full dimension 8 result compared to what you get with this dimension 6 or dimension 6 naive squared or quadratic term thing? In the case of this, which is a loop process in the standard model, you're going to have to then take into account that the loop amplitude in the standard model is down by 16 pi squared, right? So that'll affect what you conclude from the data. In the case of the standard model, the naive square is just the standard model squared, the interference term of dimension 6 with the standard model, and then the self square of the dimension 6, which is this 3 combinations of Wilson coefficients on the work cell basis. That's what people could calculate for a long time. When you do this and you actually have the full dimension 8, what do you get? Well, you get something which is very much like what was there at dimension 6, this combination interfering with the standard model amplitude. And then you basically get the self square and you get like this canonical normalization effect of the Higgs asymptotically. So it's not very dramatic. And remember that this is a 16 pi squared suppression number. So it actually significantly affects how you interpret from the data. So you can do like what we were doing before for tree level process associated with just the normal C coupling and then electric precision data and say, how does that affect the interpretation? And it's a disaster. It's this. So these are the lines again associated with some specific choices for Wilson coefficients, and then the shaded regions are the sampling of the dimension 8 stuff we can now calculate. So you should ask yourself the question, what the hell is going on here? How is this causing such a big problem? Because you think you learn something like this Wilson coefficient value is leading to some measured deviation, and actually it can be a full spectrum of possible effects that's actually leading to that deviation, which is very significantly different what you thought you would learn. Is this under control? Is this just saying the theory is not under control, and you're looking at lambdas which are too small? Well, as lambdas go bigger, of course, this does converge. That's good. But it's more to the story than just lambdas being a bit small. This is the kind of sweet spot that we want to study where this issue is present. What's happening is a combination of things. What's also happening is the Wilson coefficients themselves that are being sampled at dimension 6, the ones that are appearing in this sort of measurement compared to dimension 8 have a hierarchy in the choice that you're making. Because at dimension 6, the things involving field strengths and Higgs's, they basically get 16 pi squared suppressions and normalizable UV completions. Whereas in dimension 8, we just h dagger h times what we wrote down in dimension 6, that no longer has that 16 pi squared suppression in normalizable UV completions. So even though you're going to next order in v squared over lambda squared, which is less than 1, you're getting bigger by 16 pi squared, roughly speaking, and that's a big effect. So that's why it's leading to this big distortion. But unfortunately, what we actually have the most sensitivity for in the case of Higgs, in the case of LHC studies for the SMEFT program, is Higgs to gamma gamma and blue blue Higgs. Because the main production channel for the Higgs, and the main decay channel that's clean for us to get experimental clean results, they dominate the fits. If you look at the eigenvalues that come in the Fisher matrix and do this combined bulk analysis, it's completely dominant for what's measured at LHC. And then the left electric fusion data is super important too. So we need to basically be able to handle this sort of thing. We need to basically understand how to assign an error associated with neglected higher order terms that's affecting the channels which are so important for production and decay for these EFT interpretations of LHC. So we'll get to that in a moment, but this is a difference between loop processes in the standard model and tree level processes in the standard model, which is very significant. But you start to learn what you can actually calculate these things. You can actually quantify this is very different than that in a very well-defined way. So let me just basically take a slight diversion to say we can also do things like this pure Higgs phenomenology, which are not loop processes at a tree level again. So this is a Higgs coupling to ZZ, and this is just to get you an idea that its characters. It's not just Higgs to gamma gamma, it's not just lambda, it's all over the place. But is it going to be kinematics times geometry? The geometries will change depending on the observer we're looking at, but it's always going to be kinematics times geometry. And this is really important and kind of efficient for the experimentalists to think this way as well, and for codes to be produced for them this way, because this is standard model like kinematics. These two terms, one there and one here, are the anomalous kinematics that's there at dimension 6 for Wilson coefficients. And this one is actually empty. This is the one that was empty at dimension 6. So this anomalous kinematics first shows up at dimension 8. Same here. So this organizes your thinking so that you have to, if you're reading about acceptance corrections and learning from the data as an experimentalist, you don't just randomly, think about operators at dimension 8. You organize your thinking of, okay, what is at dimension 8 going to give different kinematic sets at dimension 6, which isn't just a rescaling of what I'm already getting. This approach basically teaches you what is like that, and you target that in your experimental study for a very careful look compared to the rescaling effects of dimension 6. The rescaling effects of dimension 6 you can pretty much do externally. Theorists can do that, right? Because it's not messing with the kinematics. It's just the Taylor expansion at next order in these geometric structures. But when you get different kinematics at dimension 8, which wasn't there at dimension 6, you better take a damn careful look experimentally to see how it's changing your interpretation from the data. And then your cuts are going to matter. So this is in the hands of Atlas now, this sort of an almost kinematics just for this very important production process for the Higgs to hold leptons. And that's the sort of thing they're doing, being a little more efficient about things. They're not just putting full codes at dimension 8 down and having to simulate everything. They're looking at targeted studies of what changes that's important at dimension 8 in terms of this very precise data set.
All right, I have a question. You say the last term, like partial mu, 8, then mu, then mu, that is from dimension 8?
Yep.
I see. But if I use this integration by part, I put derivative on the day mu. Then the first one I obtain is h day mu mu, then mu is the first one. The second
Yeah,
term,
there's equation motion reduction.
yeah.
It's
So
a subtlety.
that
You can
dimension,
write down the dimension 6 operator if you don't use the equations of motion reduction. But what will happen when you construct the full amplitude is cancellation. You can't just think of the what you're reaching towards is the fact that when you do the Warsaw basis and you do the derivative reduction, you do the equation motion reduction in the first place, you make manifest a cancellation that will happen at the amplitude level because you reduce those derivatives. If you use an alternative construction, which is like your integration by parts, you can write down a dimension 6 operator, which would then this characterization, this object would not be empty at dimension 6. In fact, these are very famous operators. They're known as Silch operators.
Yeah.
But then you combine them up into the full amplitude, and there will be a cancellation consistent with the Warsaw basis that occurs, which will cancel out that anomalous kinematics, which will first break the cancellation at dimension 8.
you are trying to say, both I'm not starting with the theory basis. I'm trying to rewrite the theory basis in terms of this Warsaw basis. Then you do not have this partial mu h then mu at dimension 6. That's what I'm saying.
In the Warsaw basis, it's not there. In another basis, it can be there. But then when you construct the full amplitude, the cancellation that you make manifest at the first step in the Warsaw basis will then happily combine up terms. And I've seen it happen. It's also happening in Higgs to Z gamma.
Okay.
And the way it happens in Higgs to Z gamma, you can understand how it happens, is essentially what you did with your equation of motion. You put the Soch operators there, is you have a redefinition of the anomalous Z coupling to lepton pairs. And then you basically get a combination of that anomalous coupling, that full combination, which is consistent with the way you chose to move the operator form, that when you actually do the full decay of the Z, exactly cancels out the anomalous vertex just for Higgs to Z gamma. So people for a while thought that Higgs to Z gamma was specially sensitive and Warsaw basis was missing it, whereas the Field Space was seeing it. They had it exactly wrong. It was that the Warsaw basis was realizing the cancellation is going to happen once they do the decay of the Z. And that happens here as well.
Okay.
So you do equation of motion reduction for a reason in effective field theories. It makes cancellations that happen at estimator element level otherwise earlier happen in the calculation.
But what I'm trying to say is the physics are not dependent on which basis you're using, right? If you found
That's
something
true.
in one basis, you found
That's
something
true,
in other
but
basis.
this is not physical yet. This is an
Okay.
offshore vertex.
Oh, you mean in the onshore cases, you,
So you have to decay the Z's. Yeah, and the fit happens on the physical observations.
okay, that makes, okay.
But this tells you something about how to organize your thinking for this anomalous vertex. Okay, good. I may talk about loop corrections and get back to the loop level processes this time. How am I doing for time? I'm running out of time.
About 8 minutes over now.
Okay, I will then instantaneously go through this and then we can just stop. You can run away and then we'll just keep going. Okay, so if this really was the organizational structure of the theory, which I'm presenting to you as being the case, you would expect it not just to help in dimension 8 terms, you would expect it to help in loop corrections as well. Does the renormalization of theory respect this geometric understanding? Do loop corrections get systematically a little bit easier with this geometric formulation? And it's a bit ironic, but we actually found this sort of approach trying to do loop corrections. Then we circled back and we went to dimensional correction. So what we tried to do was we tried to gauge fix the theory in the background field method with one XC parameter, just like Tooth did, in a way that basically had higher dimensional operators for it. And the answer that was come up with by Andreas Helsted, who's a student of mine who's in Caltech, is this form. So basically you take Tooth's gauge fixing term and you pull apart the naive squares for the gauge fixing, and you insert the metric, the expectation value of the metric, which is the hat in this case. And you do the same with the scalar field for the background field method. So you take what people have written down for the case of the standard model, you do the trivial generalization of like naive squares into basically pulled apart squares with metric insertions. And these are the gauge fixing terms that you write down. Now, what's nice about that is it's background field gauge fixing. So what comes out of that is essentially some nice word identities, which makes you understand what people were seeing in the perturbative calculations that was causing confusion. You do this variation in respect to background field gauge transformation. It's 0, effective action, in the background field method. That's the gauge fixing term, which makes this consistent. And you get a nice set of word identities, which also involve higher dimensional operator corrections. So these are constraint equations for consistency in the field theory for different endpoint functions for both the perturbative and non-perturbative expansion, the operator expansion of the theory. The photon behaves as it should. The Z identities, this is what really convinces the theory is geometric. Because what happens is in the Z identities, in the case of the standard model, it's just a mass there. When people are doing word identities with the higher dimensional operators around, it got confusing because with why is this operator Wilson coefficient appearing in the word identity? The operator itself preserves SU2 cross U1. What's going on? Is it breaking the symmetry? What the hell's going on? What you can understand from this approach is basically that what was happening was the combination that's occurring in the word identity is the geometric mass. The redefinition of the mass that's in the standard model was a linearization essentially of the field theory is then being generalized consistently into the geometric space. And it's exactly that combination of Wilson coefficient plus the Lagrangian parameters in the standard model that appears in the word identity, all consistent with your naive expectation. Good. So it works at one loop. We checked that as well. It's a non-trivial thing that it works at one loop. We checked that in these identities. Tyler did a lot of really good work here in this sort of calculation. He developed a code which lets us do this. I did it by hand, but we cross-checked and it works. And in one loop, a verification of those identities also happens. So let me finish quickly, some more time. I won't talk about this unless people ask. Let me just get this point done. So you can do this sort of stuff to calculate things like blue Higgs, which we talked about Higgs to gamma gamma before and the error associated with it. But this is the other one that's big trouble, right? It's the main production channel at C. Now you can calculate it at dimension 8. And you can also calculate a loop level, which people also have in their hands. You can get full expressions like this around in terms of both dimension 8 and loop corrections to this sort of very important production channel, inclusively at OC. So people can calculate this before. This is a cross term to do with counting normals in the Higgs field in the sky. And then this was the 90 quadratic term, which is this big Wilson coefficient there, and a big numerical coefficient there. But now you can actually calculate that dimension 8 result. But as I told you with Higgs gamma gamma, when you do the sampling, you find it's a big effect on what you do with your neglected dimension 8 terms. Same thing for Higgs to gamma gamma and blue Higgs. There's a big effect in terms of what your naive interpretation is. But when you have this sort of equation on your hands, you can ask yourself the question is, okay, it's pretty clear that we need to do something where we keep a subset of the higher order terms in our interpretation of the data. We can project onto some geometric object which has a resummation of its higher order terms. How bad is that? You know the answer, so you can check. You can look for the residual field redefinition ambiguities associated with doing that. And those field redefinition ambiguities have to go through the loop suppression of the standard model. So the gain in terms of the uncertainty that you assign adding a quadrature to neglected higher order terms when you take the subset of higher order terms, blue Higgs, and absorb it into essentially what they're fitting to is substantial. That's what this plot is showing. It goes from here to here. And the consequence in terms of inconsistencies in the field theory and your interpretation, you can also characterize numerically, and it's not a very big problem because the amplitude in the standard model is loop suppressed. This is squaring the circle of being a little inconsistent in how we interpret the data from a formal perspective, but from a practical numerical perspective, the consequence of that choice is very significantly improving what we can learn from the data. So this is the sort of thing, once you can calculate this stuff, you can actually come up with a prescription for the experimentalists for them to do this, so that they basically don't avoid completely the fact that there's neglected higher terms, but also don't disable the LHC program by doing something kind of stupid in terms of how the errors are assigned associated with those higher terms. There's a circle to square here, which I think we can do, and which we put in the hands of the experimentalists in September. They seem to be, they're doing that now. Okay, so I'm done. There's a lot we can discuss going forward. But the key point is this sentence. It really is that. I mean, the Higgs physics, when you understand it this way, it's very efficiently understood as it's a curved field space. And once you understand that and you reformulate your thinking, you can do all these sorts of calculations I've been showing you, and the time burden and technical burden associated with those calculations outside the loop stuff I showed you is really low. It's really straightforward. You just have to get the conceptual thing in your head of thinking in terms of these curved field spaces dictated by the interaction terms. And then all of this sort of work is enabled. And that's what's been happening in the subset of people that have been doing this the last 2 years during the whole COVID destroying the world. So if you jump into this, it's really easy to do. Let me just leave it at that. Sorry for being over. Are there any questions?
No question? I mean, if you're willing, some of us usually hang around afterwards after the recording is off.
Yeah, I'm happy to just,
The-
just keep going.
The
Just keep
knives
talking.
come out.
Yeah, that's fine.
So no, we're going once, going twice?
Mhm.
All right, well, let's thank Michael again for very nice talk.